All right, today we're going to tackle a classic problem from Irodov that looks pretty simple on the surface. Just an object sliding down a slope. But there's a fantastic little twist. What if that slope gets stickier the farther the object slides? Well, that one detail changes absolutely everything, and I'm going to walk you through exactly how to solve it, step by step.
So here's our game plan for this explainer. We'll start by really understanding the problem. Then we'll draw out the forces. The usual first step. Next, and this is important, I'm going to show you a super common trap that trips up a ton of students. And finally, we'll pull out the right tool for the job, a little bit of calculus, to find our answers.
Okay, let's dive right in. Before we even think about equations, we have to get our heads around what makes this sticky slope so different from all the other inclined plane problems you've probably done before.
In most textbook problems, friction is just this nice, easy, constant value. But the real world isn't always so simple, right? Imagine sliding through a patch of sand that gets deeper and deeper. The resistance would build up. Well, that's exactly the kind of scenario this problem is getting at.
So here's the official problem 1.102. We've got a bar sliding down a ramp. But the key is that the friction coefficient, mu k, isn't just a number, it's a function. Mu k equals a times x. What this really means is that the farther the bar slides, the stronger the friction gets. So our mission, should we choose to accept it, is to figure out two things. How far does it go before it finally stops, and what's the fastest it was ever moving?
So where do we even begin with a problem like this? Well, with any dynamics problem, no matter how weird it looks, you always start in the same place. You gotta decode the forces.
We're going to be really methodical about this. 4 simple steps. First, we list every single force acting on our little bar. Then, we pick a smart coordinate system to make the math as painless as possible. Step 3, we break down any forces that are at an angle, like gravity, into components that line up with our axes. And finally, we bring in the big gun, Newton's second law. Let's just focus on the motion along the slope, our x-axis. You can think of it as a tug of war. We have a go force, which is the part of gravity pulling the bar downhill. That's mg sine alpha. And we have a stop force, which is friction pulling it back uphill. So the neck force, the thing that actually causes acceleration, is just the go force minus the stop force.
And now for the really crucial part. We know the friction force is just the coefficient k times the normal force, n. The normal force, in this case, is just balancing the part of gravity pushing into the slope, so n is mg cosine alpha. We also know from the problem that k equals ax. So let's plug all of that into our F net equals ma equation. And there it is. That's our full equation of motion.
Okay, we've got our equation. Looks good, right? Well, hold on. This is where the problem gets really sneaky. If you look at the acceleration that comes out of this equation, you'll see a trap that gets almost everybody the first time around.
Let's just clean up that equation of motion a bit. If we divide everything by the mass, m, we're left with an expression for the acceleration, w. And I want you to look really, really closely at it. Do you see it? That x sitting right there? That means our acceleration isn't some constant number. It's actually changing as the bar slides.
And this, right here, is the biggest mistake you can possibly make. As soon as you see that the acceleration depends on position, a big red flag should pop up in your brain. All those trusty old kinematic equations you learned, v equals v naught plus at, you have to throw them out the window. They are completely useless here because they only work when acceleration is constant. We need a different tool.
I tell my students this all the time. The most important skill in physics isn't just memorizing formulas, it's knowing when you can use them. The key to cracking this problem, and so many others, is that first moment of recognition. That, wait a minute, things are changing here, so the simple rules don't apply.
So if all our basic kinematic equations are out, what's left? Well, whenever you have things that are changing, there's one tool that never lets you down. Calculus. It's time to upgrade our toolkit.
So here's our secret weapon. It's a really clever trick that uses the chain rule. We all know acceleration is dv dt, the change in velocity over time. But our formula for acceleration has an x in it, not a t. So we need a bridge. We can rewrite dv dt as dv dx times dx dt. And what's dx dt? Well, that's just the definition of velocity, v. This gives us a new, super powerful way to express acceleration. A equals v times dv dx. And bam! That's the breakthrough. We have 2 different ways of describing the same acceleration. One came from our force diagram, and the other came from this calculus trick. By setting them equal to each other, we get this amazing equation that connects velocity directly to position, and we don't have to worry about time at all. This is the key that's going to unlock the whole problem.
Okay, take a deep breath. The conceptual heavy lifting is done. We have built our master equation. Now all that's left is to actually use it to find the two things the problem asks for, the total stopping distance and that maximum velocity.
First up, let's find that total distance. What we do is shuffle our equation around so all the v stuff is on one side and all the x stuff is on the other. Then we integrate both sides. And we have to think about our start and end points. The bar starts at position 0 with 0 velocity, and it ends at some final distance, let's call it x stop, where its velocity is also 0. Those are our limits.
And after you do the integration and solve for that x stop, look at what you get. All that work, and it boils down to this surprisingly clean and simple result. The total distance just depends on the angle of the ramp and that friction constant a. Pretty neat, huh?
Okay, part 2, maximum velocity. Just think about the bar's journey for a second. It starts from rest, so it has to speed up. But we know the friction keeps getting stronger, so eventually it has to slow down and stop. So there must be a sweet spot in the middle where it hits its top speed. And that peak velocity happens at the exact instant the acceleration flips from positive to negative. In other words, when the net force and the acceleration is exactly 0.
And the math for this part is actually pretty easy. We just take that original formula we found for acceleration, set the whole thing equal to 0, and just solve it for x. And that gives us the exact place on the ramp where the bar is moving the fastest. Now, stop for a second and look at this. This is what's so beautiful about physics. Compare the position where the velocity is max to the total stopping distance we found before. It's not just some random point. It's exactly, precisely halfway along its path. How cool is that? It's such an elegant result.
So, we did it. We cracked the problem. But the real point of doing these kinds of problems isn't just to get an answer. It's to build a strategy, to add a new tool to your problem-solving toolkit that you can use on other problems down the road.
So let's boil it all down. This is your new superpower. It's a 5-step plan for any problem where the force depends on position. 1. Start with forces. 2. Find the acceleration. 3. Check, and this is the most important step, is that acceleration constant or not? 4. If it depends on x, you pull out your new secret weapon, w equals v dv dx. And 5. You integrate to get your answer.
And that's really how you break down a tough problem like this. The technique we use today is so useful. So my question to you is, where else in physics have you seen forces that change depending on position? Think about it for a second. Thanks for tuning in.